Welcome to Lecture 7 of my series on PH 4105 Advanced Mathematical Physics. We have been discussing differential geometry here, and in the last lecture we introduced the differential geometer's version of vectors. To be more precise, we talked at length about what I am calling the algebraized definition of a vector, where we started with curves, talked about tangent vectors to curves, and then ended up defining tangent vectors to a manifold at a point as some kind of machine, so to speak, which changes functions to numbers with certain special properties which make them look a bit like derivatives. So let me just remind you quickly about what we talked about in the last lecture. We started, of course, with a definition of a curve, and a curve here is defined to be a smooth map from an open subset, typically an interval, I of the real line, to M. Let me remind you once again, I've done that several times in the last lecture, but repetition doesn't hurt in this case, that the curve to us is the map which carries points on an interval of the real line to the manifold, and not the set of points on the manifold themselves. That, of course, is the image C of I of the curve that you can see in orange in your graph. Now, given a point CT0 on the manifold, on the image of this curve C, the tangent vector to the curve C at the point CT0 is basically a map which allows you to figure out how fast an arbitrary function will change if you were to move along the curve through this point CT0, and in fact it will tell you how fast is the function f changing exactly at CT0. So formally the definition goes like this. C prime T0, this so-called tangent vector to the curve C at the point CT0, is a map from C infinity M to R. The set of all smooth functions of the manifold is mapped to the real line by this. And when you feed C prime T0, this particular map, the function f, what you get basically is this quantity. You evaluate f at a point C of t, which is very close to the point C of t0. T is taken to be very close to t0. Find out how much the function increases from its value at ct0. If you do that, divide by the interval t minus t0 and take the limit as t goes to t0. Of course, a more formal way of defining this would be to say that this is nothing but the derivative of the pullback of function c star f composed with c, which is a function from the real line to the real line. That is, it's a function from the interval I to the real line, evaluated at the point t0. So basically what C prime t0 does is tell you how fast does the function f change at the point ct0 of the curve when you move along the curve. Now this leads to certain very simple properties by direct calculation. We had verified these properties earlier. Acting on a linear combination AF plus BG, C prime T0 gives A times C prime T0 acting on F plus B times C prime T0 acting on G. In other words, C prime T0 acts like a linear map on the space of functions. What makes it like a derivative, apart from the fact that it is a rate of change, is this second property, that C prime T0 acting on a product F times G gives you two terms. One term is one in which C prime T0 gets to act on G. It's multiplied by the value of F at the point CT0. The other term is C prime T0 acting on the other function F multiplied by the value of G at CT0. Now this is the property which looks very much like the derivative property called the Leibniz property, And in fact, it goes to show that what we are dealing with here is a kind of derivative. As I said a while ago, what we did earlier was to define a general notion of a tangent vector Vp at a point P belonging to M by modeling it on this notion of a tangent vector to a curve. This map Vp maps C infinity M to R just like C prime D0 did, and it satisfies the linearity property and this property of acting like a derivative on the product. Vp acting on Fg is f of P times Vp acting on G plus Vp acting on F times G at P. Now what we claimed in the last lecture was the following. If you take the set of all tangent vectors to M at the point P and call that TPM, this becomes a linear vector space. Of course, in order to do so, you need to define what you mean by addition of two vectors or two elements of TPM and multiplication of an element of TPM by a scalar. And the definition here is a simple, obvious definition. Vp plus Wp acting on F is defined to be Vpf, which is a number, added to Wpf, another number. Similarly, AVP, this new tangent vector acting on F, would give you A times Vp acting on F, where A is any real number. We have verified in the previous lecture that Vp plus Wp and AVP defined in this particular manner are tangent vectors at the point P. That is, they satisfy the basic defining properties of a tangent vector at a point P. What we did not do, but left as an exercise to you, the viewer, is to show that all the basic defining properties of a linear vector space are obeyed by TPM. I hope you have verified this to your satisfaction. Now, when we talk about a vector space, a natural question to ask would be, what is the dimensionality of that vector space? And the answer to that is in the following claim. If M is an n-dimensional smooth manifold, then TPM, the set of all vectors, tangent vectors to the manifold M at the point P, is a n-dimensional vector space. Now, in most of today's lecture, we will be proving this particular statement. But before we go there, let me go back to the defining properties of tangent vectors at a point P and use them to prove a rather interesting and important result, which sort of once again reinforces the notion that these tangent vectors are somehow connected to differentiation. The property I am referring to is, what does this tangent vector Vp do to a constant function C? And to see that, let me work this out in a few steps. Here, Vp is acting on C. Note that C is not a number, it's a member of C infinity M. It's a smooth function, a function whose value at every point of the manifold is a constant C. But you can always write this function C as a product of the number C, a real number C, and the function which I denote by 1, which is a smooth function which returns 1 for all points on the manifold. So note that C here is actually different from the C here. This C is a function, this C is a real number. Of course, using the linearity property of tangent vectors, this immediately translates to C times Vp acting on 1. So you want to figure out what Vp does to any constant function. And at this stage, I don't think there should be any prizes for guessing what the result is, but we still have to prove the result. What you get is C times Vp acting on the function 1, the constant function whose value is 1 at every point on the manifold. Now, in order to do this, we are going to use a second property, that is a derivative property of a tangent vector. Vp acting on 1, the function, is actually equal to Vp of 1 times 1. Here note both the ones are actually smooth functions, not real numbers. Of course, a function which returns 1 at all points multiplied by itself will also give you the same function. But now we can use the derivative property. This is a product of two functions, so the result will be the value of the first function at the point P times Vp acting on 1, the function, plus Vp acting on 1, the function, which is this function, times the value of the other function at the point P. Of course, the values are always 1. So we end up with Vp1 being equal to twice Vp1, which immediately tells you that Vp1, Vp acting on the constant function 1 has to be 0, and hence Vp acting on any constant function C has to be 0. This, as I indicated before, is pretty obvious, but it also ties up neatly to the fact that our tangent vectors are connected to differentiation in a big way. With this out of the way, let me now turn to the question of the dimensionality of this linear vector space TPM. And in order to substantiate our claim that TPM is an n-dimensional vector space, we will have to make use of charts and their associated coordinates. Actually, what we will use are special kinds of curves which coordinates give us, so-called coordinate curves, and tangent vectors to the coordinate curves. So let me remind you of the notation. If u phi is a chart on M, then u is a subset of M and phi is a map which maps a point P of u to a bunch of real numbers, x1, x2 up to xn. And of course, these x1, x2, xn's depend on P, and so they define for you functions x1p, x2p, x3p, etc., which are all smooth functions acting on a point on the manifold and giving you a real number. So all of these are members of C infinity M. Now, given these coordinate functions, we can define a coordinate curve. The ith coordinate curve through P, a point on the manifold, is defined to be the curve Ci. We are talking about the ith coordinate curve, so this is C suffix I, which maps the interval a comma b to R, where this interval contains the number 0. And this curve has this property that Ci at 0 is the point P, and Ci at t is given by this rather complicated looking set of numbers. But that actually is pretty straightforward. All you are saying is, at the point P, you have coordinates x1p, x2p, etc., xnp. So let's take a bunch of coordinates which are essentially the same bunch, except that the ith one has been increased by t. Everything else are the same as the coordinates that P had. Only the ith coordinate is bigger. And phi inverse, of course, takes you from this bunch of coordinates back to a point on the manifold. So Ci at t, which has to be a point on the manifold, is simply the point you would get if only the ith coordinate were increased by t, all the other coordinates staying fixed. So this is a curve on which, as t varies, only the ith coordinate changes, all the other coordinates retain their value. And what we do now is to denote the tangent vector at P. Remember, this curve, of course, passes through P. If you put in t equal to 0, you are going to get the coordinates of the point P here. So phi inverse acting on that takes you back to the point P. And the tangent vector at P to this ith coordinate curve is denoted by something which looks very similar, which looks like a partial derivative symbol that we used in first year in college, and is denoted. It is denoted by del xi with P written down to ensure that you remember that this is a tangent vector at a point P. Now, if you had not seen these ideas before, much of this can seem pretty unfamiliar and strange. Let me assure you though that this is really not very different from what you have known all along. To illustrate that point, let me show you a few examples now. The first example I'm going to consider is a very, very simple one. We are going to talk about a plane R2, and here we are going to use the standard coordinates on R2, that is Cartesian coordinates. Let me remind you that here the chart u, phi has a domain u which is basically all of R2 itself, and the map phi that you use for this chart is simply the identity. That is, it takes a point xy of R2 and maps it to xy. Now, for this coordinate system, let us see what the coordinate curves mean. Here is simplicity itself. If a point P is given by the coordinates x1 and x2, and of course, the point on the manifold is really the pre-image under phi of these coordinates. But remember, here we are using identity as the map phi, so phi inverse is also the identity. So basically the point P here is just the point with coordinates x1, x2. Or in R2 it's just the point x1, x2. Notice that in this case, the point with coordinates x1, x2 and the point x1, x2 happens to be identical, but that's of course because we are using this special set of coordinates. Now, in order to figure out the 1th coordinate curve here, what I need to do is to see how the pre-image of these coordinates are going to change when you change only the first coordinate by t. So let us take a look at this point. This has coordinates of x1 plus some number t and x2 staying the same. As t runs over a whole interval, this point of course moves when from a negative value of t, if you go to a positive value of t, this is how you move, and that of course traces out a straight line. This is a straight line through the point P parallel to what we call the x-axis. Obviously, very, very similarly, as you move parallel to the y-axis, what you get is the other coordinate curve, which is made of points which are pre-images. In this case, pre-images of course mean the same thing as the point itself of x1, x2 plus t. Now what about the tangent vectors? The coordinate tangent vectors here, del xi's, are basically what tells you how fast the vector, a function will change. Any function, including coordinates, will change as you move along a coordinate curve. So as you move along the first coordinate curve, this blue line here, you are essentially figuring out how fast will a function change when you move from this point along this direction. And the way we depict this in a picture is of course using an arrow, and this arrow is our del x1 at the point P, and you should all be certain here that this is something very familiar. This is nothing but what we call I hat, at least what we used to call I hat in our first year in college or even high school. What about the second coordinate curve and its tangent? That tries to measure how fast functions will change as you change only the second coordinate, that is as you move along this black line here, and this is the arrow which depicts that quantity. So this is del x2 at the point P, and once again this is nothing other than our familiar j hat vector. So at least for Cartesian coordinates, these notion of coordinate basis of coordinate vectors or is really very familiar. All you're really saying is that all you're really getting back here are the familiar I and j vectors, the basis vectors for the Cartesian coordinate system. Let us next take a look at something slightly more complicated, but let me assure you it's not much more complicated. It's again R2, but this time using polar coordinates. Here the point P has polar coordinates r and theta, so the point itself is a pre-image under the chart phi, the polar coordinate chart, of these coordinates r and theta. R and theta here play the role of the first and the second coordinate respectively. So what about the coordinate curves? The first coordinate curve is one which you get when r changes by t and theta does not change at all. And there, what you of course have is that you're moving along this blue line here. A typical point would be something like this, which is the pre-image under this chart of r plus t, theta. Once again, the geometry is very clear. R is going to increase by t, so you're moving radially outwards. Of course, t could be negative, which would mean that you would be somewhere closer to the origin than the point P. As t changes from negative to positive values, you move along this line, and in particular at t equal to 0, you are at the point P. The tangent vector to this curve is something which measures how fast function changes when you move along this blue line, and is depicted, of course, by a vector, an arrow, which is pointing along this blue line. So this red line here is del r at the point P, which once again should be pretty familiar to all of you. This is the r hat, the unit vector in the radial direction, which should be familiar from at least first year of college, if not high school. Now what about the second coordinate curve in this case? Here you're going to change theta and not change r. So a typical point would be somewhere here, moving on a circular arc of radius r, and this is the point which is the pre-image of r, theta plus t. So geometrically, of course, this is a point on the circular arc of radius r centered at the origin, such that this particular angle here is given by t. So if you are talking about how things change when you are moving right away from this point, you are going to move along the tangent to this curve, and this exactly is what del theta at point P is. So once again, this should be pretty familiar to all of you. This is a cross radial vector, although there is a point, it's really not theta hat. It's in the direction of theta hat, but its length actually is not unity. In particular, the length depends on what the value of r is. Now, why does that happen? That's also pretty easy to understand. After all, when you change t, for this curve, what you're doing is you're moving to an angle which is given by the amount t. But how much you move, that depends on how big the circle is. So for a larger value of r, you are actually going to move a larger distance. So if you were to take a point here at a larger value of r, then del theta at this point, let's say q, is going to be longer than del theta at the point P. So here, the length of the vector depends on how far out from the origin you are. That doesn't happen for del r for the obvious reason that no matter how far out you are, if you change r by t, you are essentially moving the same distance away, namely a distance t away from the origin. So the radial vector, okay, pardon my drawing, I have inadvertently drawn a longer vector, but I should really draw a vector of the same size. Del r at the point q is the same length as del r at the point P, whereas del theta at the point q is longer than del theta at the point P. Now, having said that, let me warn you about something. At this stage, we have not really developed the machinery where we can talk about lengths of vectors on an arbitrary manifold. In fact, we have no notion of lengths and angles, at least in the differential geometry that we have learned so far. So what I am doing here is I am borrowing from ordinary notions of lengths and angles from 2D geometry. And at least in this case, because we are in 2 dimensions, we can definitely do that. So when I say that del theta increases in length as you move away from point P to point Q, which is further out from the origin, I am actually using a notion of length, which I am already familiar with, but not something we have developed at least during the course of these lectures. We will talk about the notion of length on manifolds later. It's only special kind of manifolds on which we can do that. It so happens that on R2, these notions of length coincide with our ordinary geometric notions. So there is no harm in actually using these notions. Of course, another notion that we have not developed so far is that of an angle, which is tied down to this notion of length. But if you think of it, it's also pretty easy to understand from our ordinary notions why del theta and del r at the same point are actually perpendicular to each other. But once again, these are issues which we are going to formally cover only once we have the machinery to deal with this. For the time being, what is important is to realize that del theta and del r are basically the same thing as the kind of unit vectors we have always been used to. For our final example of coordinate curves and tangents to coordinate curves, let us leave flat land and go on to a very familiar curved manifold. Once again, the word curvature is something I am using in the standard class 10 geometrical sense. We have not introduced enough machinery to talk about curvature properly yet. This manifold is a very familiar one, as I said. It is nothing but S2, the two-dimensional sphere. And we are using spherical polar coordinates, things which physicists use all the time, on this manifold. So a typical point P here has coordinates theta and phi. I apologize that my usage of phi is a bit dual here. I'm using phi, the straight phi, to denote the chart which maps the point to the spherical polar coordinates. Curly phi here is my angular coordinate phi, which is the familiar notation that physicists use all the time. P is of course the P image of this point. In other words, P is the point whose coordinates under the spherical polar coordinates chart are the numbers theta and phi. What about the coordinate curves? They are also pretty straightforward. If you change theta and theta alone without changing phi, you are moving along this blue line here. This is the first coordinate curve in this case, and it's nothing but our old friend, the meridian line passing through the point P. Something which should be familiar to all of you from your geography classes. The tangent vector to this curve at the point P is one which points along this curve here. It measures how fast a function changes as you move along the blue curve through this point. What about the second coordinate curve? Is the one which you get when you change phi and phi alone. So this is your second coordinate curve. I have depicted a typical point in this curve, the P image of the point theta, phi plus t for some value of t. And the corresponding tangent vector is one which essentially measures how fast things change as you move along this line. This curve again should be very familiar from geography. This is nothing but a line of latitude. So these are our two basis vectors, two tangent vectors, del theta at the point P and del phi at the point P. Once again, if we borrow from our high school notion of what a length is, it should be pretty easy to understand that the length of del del theta does not change as you move the point P and place it at different points on your manifold. Since in each of these cases, as you change t, you are moving along one of the meridian lines, and all meridian lines have the same radius. They are circles with the radius which is equal to the radius of your sphere. If you are talking about a unit sphere, they all have radius 1. On the other hand, del del phi has a length which depends on where you are on the manifold, simply because when you change phi and phi alone, you move along circles of latitude which grow smaller and smaller in radius as you move closer and closer to the North Pole or to the South Pole. So the length of del del phi will depend on the value of theta, which dictates how large the radius of the second coordinate curve, this circle of latitude, is going to be. I hope these examples have sort of convinced you that the notion of coordinate curves and tangent vectors to the coordinate curves is not really a very alien one. In fact, you have been using these coordinate curves and the tangents quite a lot in your earlier studies in physics. Now, you may have noticed that I have used the word basis vector a few times in describing the tangent vectors to coordinate curves. Now, there is a reason for that. It turns out that if you take all the coordinate curves through a particular point and consider their tangent vectors, you actually get a basis for the linear vector space TPM. This is something we will prove in the rest of this lecture. But before we get to do that, let us take a deeper look at the properties of these coordinate tangent vectors. The first property that we are going to take a look at is exactly what does del del xi at the point P do to a function f. Now for this, all we have to do is remember that del del xi at the point P is simply notation for the tangent vector to the ith coordinate curve ci at the point P, and the way in which you figure out what del del xi P does on f is the way in which any tangent vector to a curve acts on a function, which is figure out how fast the function changes as you move away from that particular point. Here, of course, the point P is what you get when you put t equal to 0. So, you're really looking at the limit as t tends to 0 of this quantity, the ratio between the value of the function at ci of t minus the value of the function at ci of 0 in the numerator and t minus 0 in the denominator. Now, let me remind you once again that ci of t is basically the point on the manifold whose coordinates are essentially the same as the coordinates of the point P, except that the ith coordinate has been changed by t. So it's the point given by phi inverse of this bunch of coordinates, x1p, x2p. All of them stay the same. It's just the ith coordinate xip which has been increased by t. So phi inverse of that gives you ci of t, and you are going to do f of that. So it's basically f composite phi inverse, this composite function which acts on this bunch of coordinates. F of ci 0 is nothing but f of p, and is certainly the same thing as f composite phi inverse acting on a very similar bunch of coordinates, but this time these are all just the coordinates of the point P. So you subtract these two things from each other and divide by t. Let me point out that f composite phi inverse is a pretty familiar thing to us from earlier lectures. This is the proxy function capital F, the proxy function for small f according to the chart u comma phi, which maps phi of u to r. So this is a map on which ordinary calculus can be used. Remember, phi of u is a open subset of Rn. So we have a function from Rn to R, or rather an open subset of Rn to R, which is amenable to doing calculus. And that is why we had used this proxy function earlier to decide on the differentiability class of small f. Let me remind you, a function small f is said to be differentiable of class CR at a particular point P if the proxy function f composite phi inverse, which is a map from phi of u, an open subset of Rn to R, is differentiable of class CR at the point phi of P. Now coming back to this particular expression, it's pretty easy to see that this thing is something pretty familiar to all of us. After all, what we have is a function f composite phi inverse of n real numbers. All we have done here is changed one of the arguments of this function f composite phi inverse, the ith one, by an amount t, found out how much the function changes, and divided that change by the change in the argument, that is by t, and taken the limit as t goes to 0. This is nothing but the partial derivative with respect to the ith argument of the function f composite phi inverse, evaluated at the point x1p, x2p up to xnp, that is at phi of p. Now, while we are used to using the notation del del xi to talk of the ith partial derivative of a function, we are not going to use that here because we already have used the notation del del xi of p for the tangent vector corresponding to the ith coordinate curve. But this should make it easy for you to understand exactly why we chose this notation. Del del xi at p, the tangent vector to the ith curve acting on a function f, gives you exactly the ith partial derivative of the proxy function evaluated at the proxy point phi of p. I am writing capital Di for the partial derivative just to distinguish this from del del xi, which for us is the tangent vector. Of course, what we are saying here is the tangent vector essentially behaves like the ith partial derivative, at least at the level of the proxy function. We get an important special case of this result when, instead of an arbitrary function f, we use a specific function, the jth coordinate function. Now it's easy to understand what is going to happen in this case even without the help of this formula. After all, a tangent vector to a particular curve measures how fast a particular function is going to change as you move along the curve. Since only the ith coordinate changes, nothing else changes, in the coordinate curve, it's pretty easy to see that if the function that you're looking at is a jth coordinate function and j is not equal to I, then you should expect to get a 0. Let us just verify whether that happens by using the formula. If I take this formula and instead of f just use xj, what you're going to calculate ultimately is limit as t goes to 0 of this ratio. 1 over t times the difference of xj composite phi inverse at this bunch of coordinates with the ith coordinate changed by t and the original value of xj composite phi inverse at the coordinates of the point P itself. Now if j is equal to I, then this particular result is going to be simply xip plus t, and this of course is just xip. So the difference in the numerator is t, and therefore what you are doing is you are calculating the limit as t goes to 0 of t by t. That this is when j is equal to I. So you get 1 for the limit when j is equal to I. And if j is not equal to I, both of these are exactly equal to the same thing, namely xj at p, the jth coordinate of p, and therefore the difference in the numerator vanishes and you end up with 0 for the value of this limit. So the final upshot of this is del del xip acting on the function xj is going to be 1 if j is equal to I and 0 if j is not equal to I, and that is something we denote by delta ij, the standard Kronecker delta symbol. By the way, we very often write this del del xi at the point P acting on f is often written instead as del f del xi at the point P. And if we adopt the same convention, this thing is going to be del xj del xi at P. And if you remember your high school calculus, it should be easy to understand why this notation is nice. After all, this suggests itself using elementary calculus from high school that this should be 1 if j is equal to I and 0 if j is not equal to I. Now this result is extremely important in the proof of the fact that the tangents to the coordinate curves provide us with a basis for TPM. One of the first things that you need to check for a set of vectors to be a basis for a vector space is that they are linearly independent. That is the only way in which you can linearly combine them to get the null vector is to give them all coefficients of 0. Now, the proof that del del xips as I runs over 1, 2, 3 all the way up to n are linearly independent follows simply from this result that del del xip acting on the function xj gives you delta ij. All you have to do is to take a combination ai del del xi of p. Here summation over the index I, which is repeated, is assumed. So this really means a1 del del x1 at p plus a2 del del x2 at p all the way up to an del del xn of p. If this is 0, then of course this gives you 0 on every function. That's what this vector being 0 means. In particular, it will give you 0 acting on the function xj. But we already know that del del xip at xj is delta ij, and this sum ai delta ij, this of course is a sum over I, is simply aj, and therefore aj has to be 0 for each and every j. This establishes that the set of tangent vectors to coordinate curves del del x1p del del x2p up to del del xnp is a linearly independent set. In order to qualify as a basis, the next thing that you have to show is that this is a spanning set. That is, every element of TPM can be written down as a linear combination of the del del xips. So for every vector Vp belonging to TPM, you have a bunch of real numbers C1, C2, C3 up to Cn such that you can write Vp as a combination of the del del xj's with cj as coefficient. That is, you can write every Vp as ci del del xi at p, c1 del del x1 at p plus c2 del del x2 at p plus c3 del del x3 at p up to cn del del xn at p. Now this is a claim that we are making at this stage. The proof of this claim is a bit involved, and it will take us some time to go through the entire proof in detail. So I've decided that I will leave the proof for a later video. In this lecture, we are going to assume that this is true and go ahead. Now, if we assume that this claim is correct, that is, Vp is of this form, it is actually pretty easy to find out what the coefficients Cj are going to be. All you have to do is take this form for Vp and apply it on a particular coordinate basis function. Let's say on the ith coordinate function, xi. Now, Vp acting on xi is going to be Cg del del xj of p acting on xi. But we already know that del del xjp acting on xi is delta ji, So this sum is simply Cj times delta Ji, of course sum over J, and this, using the simple property of the Kronecker delta symbol, becomes Ci. So the ith coefficient in an expansion like this, if Vp can be written like this, has to be Vp acting on the ith coordinate function. Or in other words, provided you accept this claim as correct, what we have shown is Vp, every tangent vector, can be written down in the form Vpxi del del xip. The Vpxi here are of course numbers which you get when the tangent vector Vp acts on the ith coordinate function, and these numbers are going to be the coefficients for the vectors del del xip. Now, while this proof that Ci is Vp of xi is pretty convincing, you must realize that the major gap in the argument here is that we have not yet established that this can be done for all vectors Vp. Pending that proof, it's pretty easy to see that Vp, if it is at all a linear combination of the del del xjp's, has to be of this particular form. It has to be Vp acting on xi times del del xip. As I have said, for the rest of this lecture, we are going to assume that this result is correct. It is, but you must realize that we have not completely proven this result as yet. That proof is going to come in the next lecture. Indeed, the proof will not only show that it is possible to write down every tangent vector as a linear combination of the del del xip's, during the course of that proof, this particular form for Vp is going to emerge automatically. Pending that proof, we are now going ahead and look at what consequences this particular form is going to have. One immediate consequence is a very obvious corollary. Every tangent plane of an n-dimensional manifold, that is, every TPM for different points P on M, must be an n-dimensional linear vector space. After all, if you have an n-dimensional manifold, then every point P belongs to the domain of some chart or the other, which maps the points of the domain of the chart into an open set in Rn. So you have n coordinate functions, and corresponding to the n coordinate functions you have n coordinate curves, and this gives rise to n tangent vectors to the coordinate curves, which by now we are justified in calling the coordinate basis vectors. And because you have n coordinate basis vectors, TPM is n-dimensional. Let us now take a look at another consequence of this particular form. Remember, we started out by looking at tangents to curves going through a particular point. And then we generalized that notion to talk about tangent vectors at a particular point P, without referring to curves. The way we framed this transition from tangents to curves to just tangents at a point P made it seem that we are generalizing the notion of tangents to a curve. It was obvious that all tangents to curves passing through point P would be tangent vectors, because it was their properties which were being generalized. But it did seem at the stage that by doing this, we have actually gone to a bigger class of objects. That is, it seemed at least that there might be tangent vectors at a point P, which may not be tangents to some curve going through point P. It turns out that that is not right. All tangent vectors are actually tangents to curves. And this is what we are going to establish using this formula that Vp is Vp of xi del del xip, summed over I. To see this, all we need to do is, for any given curve C in M, that is C being a map from an interval I of the real line to M, its tangent vector at the point CT0 will be given by this very formula, except that you have to use C prime T0 acting on the ith coordinate function times del del xip. I will not keep on mentioning sum do y every time. That is to be taken to be understood. So C prime T0 is C prime T0 xi del del xi at Ct0. But now remember, C prime T0 at xi, by definition of the tangent vector to a curve, is simply the derivative of the proxy function xi composite C. That is, of the ith coordinate function as you move along the curve. And this has to be evaluated at the value T0 of the argument T. Hence, C prime T0, if you replace C prime T0 acting on xi by this, becomes d dt of xi composite C at T0 del del xi Ct0. Note that this d dt of xi composite C at T0 is nothing but the rate at which the ith coordinate function changes as you move along the curve, xi composite C simply being the ith coordinate of a point on the curve. Now, if we start with an arbitrary Vp, of course, because we have now seen that del del xip form a basis of TPM, Vp can be written down as a linear combination of del del xips, let's say Vi del del xip. Then, Vp will be the tangent to a curve C if these numbers match Vi. That is, if ddt of xi composite C at the point T0 is Vi. Now this puts some restrictions on the function xi composite C. In other words, it tells us that the value of xi composite C at T must be equal to the value of xi composite C at T0 plus this number Vi into T minus T0. This is nothing but the Taylor series that we are using here, plus higher order terms involving higher powers of T minus T0. So this, of course, tells us that the ith coordinate of a point on the curve has to obey this equation, so there are infinitely many possible choices. Each of these choices will end up giving you a curve, and each of these will have Vp as a tangent at Ct0. In particular, I could have just stopped here and just looked at a curve which obeys xi composite C at T is xi composite C at T0 plus Vi into T minus T0. That curve will definitely have the vector Vp as tangent at the point P, that is at C of T0. So, what we have established is that every tangent vector at a point P is a tangent to a curve going to the point P. In fact, not to a curve going to the point P, but infinitely many curves, each of which share the same tangent. If you recall the geometer's definition of a tangent vector, it's actually these infinitely many curves together which form an equivalence class, or the germ which is equivalent to the tangent vector. We are going to discuss the geometer's definition in some detail in a later lecture. I'm just throwing this in here as a nugget to remember. The last of the consequences of the fact that the del del xips form a basis set for TPM is going to involve the third kind of notion of a vector, the faces one. If you remember your notion of vector from any slightly advanced physics textbook, you are likely to remember it as a bunch of numbers or an object which is described by a bunch of numbers which transform in a very particular manner when you change your coordinates. This is what I've been calling the physics definition of what a vector is. It turns out that once we have established that the del xips form a basis for TPM, this is something which you no longer have to take as a separate definition. This is an immediate, simple consequence of this fact. In order to see this, let us see what happens when you change coordinates. That is, instead of using u phi, a particular chart, you use a different chart, v chi. Let u phi and v chi both be charts on M, and let the point P belong to the intersection of U and V, so that at the point P, we are free to use either the coordinates provided by phi, which are the coordinates x1, x2 up to xl, or the coordinates provided by chi, y1, y2 up to yn. So these are two different sets of coordinate functions, one for each chart. Now the vector space TPM now has two different bases. One is the set of basis vectors provided by del xi p's, I running from 1 to n. The other is the set of basis vectors provided by del yi p's, again I running from 1 to n. An immediate question that would arise is, how are these two different basis sets related to each other? And the answer to that is very, very straightforward. It follows directly from the fact that every vector Vp is Vp acting on xi times del xip, summed over I. So in particular, del yi acting at P is nothing but del yip acting on xj times del xj. Now, as I have said before, the notation for del yi acting on xj is del xj del yi. This is not really a partial derivative of the function xj with respect to yi, simply because xj's are functions of points on the manifold. They are not functions of the y's really. However, what we really do here is write the xj's using the proxy functions, that is xj composite chi inverse, to get functions of y's and then partially differentiate that, work out the ith partial derivative of that, which is what we are writing as del xj del yi at P. Remember, this is exactly what we did for an arbitrary function f. So the partial derivative is really the partial derivative of the proxy function. But remember, when we talk about change of coordinates, we really write the new coordinates y as functions of old coordinates x, or vice versa. So what we are really talking about there are the proxy functions. So this is really the kind of derivatives that we meet when we talk about transformation of coordinates. And so this is really a rather familiar result, or at least should be a familiar result to anybody who has done a phases version of tensor analysis. So del yi at P is ultimately given by Cij del xjp, where the coefficients Cij are nothing but the vector del yip acting on xj, which is written as del xj del yi evaluated at the point P. So you see, the basis vectors for the new set are related to the basis vectors of the old set via a linear combination, and the coefficients of the combination are partial derivatives, actually the partial derivatives of the proxy functions corresponding to the jth old function. I am calling phi the old chart and chi the new one, with respect to the ith new function. Now this should be, as I have said, very familiar to anybody who has studied the definition of a vector according to a standard phases tensor analysis course. There is a problem, however. After all, vectors are defined in the phases parlance to be something which can be described by n numbers which transform linearly, but there the coefficients are partial derivatives of the new coordinates with respect to the old ones. That is, you expect del yi del xj and not del xj del yi. Why that difference occurs is actually pretty easy to figure out. Remember, here we are talking about the basis vectors. In a phases definition, typically we talk about how the components of a vector change, and therein lies the difference. As for the components, the ith component in the new coordinate system, that is the coordinate system provided by the chart capital V, chi, is V prime I have used the prime to denote that these are the so-called new components. This must be simply the vector Vp acting on the ith coordinate function here, but the ith coordinate function provided by the chart capital V comma chi. So Vp acting on yi. However, we already know that Vp, the vector, is Vp acting on xj times del del xjp. This Vp acting on xj, these are nothing but our old components, that is, something which we would write in Fair's language as Vj. Now, this expression Vp xj or Vj times del del xjp acting on yi is simply Vj with del del xjp acting on yi. Vj's are just numbers, they come in for the ride. And so what we have is del del xjp acting on yi, which, as we have said, our standard shorthand is del yi del xj. Just to remind you once again, this yi notation here looks like a partial derivative, and it is the jth partial derivative of the function yi composite chi inverse. Be that as it may, ultimately we can write this whole expression V prime I, the components in the new coordinate system, as linear combinations of the Vj's with the coefficients being del yi del xj at p. This is the familiar transformation law for the components of a vector. Let me emphasize once again that we did not have to impose this as a new definition. It just followed from the way tangent vectors are defined in differential geometry. In particular, from what I have been calling the algebraized way of defining vectors. Let me remind you once again, there has been a major gap in our proof so far. We have not yet established that every vector Vp can be written down as a linear combination of the del del xi's. That is the first thing I am going to show you in my next lecture. And then we are going to take a look at what happens when you move vectors from one manifold to another by using smooth functions, something called a push forward. And then we are going to look at further properties of vectors and sets of vectors, these tangent planes, and more complex entities like vector fields, covector fields, and so on. But all these will have to wait for later lectures. Bye for today.